The most advanced spacecraft do not move at all. They stand perfectly still while the universe moves around them. A visionary physicist once said the universe is not a stage upon which we move, but a fabric we can influence. This video will give you a complete understanding of a new form of propulsion that bends the rules of reality itself. We will uncover the principles that allow a ship to warp spacetime right in front of it, making the vast emptiness of space contract and expand on command. How is it possible to travel without actually going anywhere, and what does it mean for our future among the stars? What does it truly mean to travel a sailboat does not push against the ocean to move forward? It sets its sails to catch an invisible force, the wind, and lets that external power carry it along. This elegant principle holds a profound secret for the future of space travel. For decades, our only idea of propulsion was to push against something. Chemical rockets throw mass out the back as fast as possible, creating a reactive thrust that shoves the craft in the opposite direction. Ion drives are more refined, using electric fields to accelerate particles to incredible speeds, but they still operate on this same fundamental principle of action and reaction. The problem is, you have to carry your push with you. The fuel, the reaction mass, it all adds weight, creating a vicious cycle where you need more fuel to push the fuel you are already carrying. This makes reaching even a fraction of light speed a practical impossibility. We have been trying to build a faster engine when what we needed was a completely different idea. Dr. Elena Vance, a leading theoretical physicist, puts it perfectly. She says propelling a mass through space is inherently inefficient. The future is in propelling space itself. This is the foundational shift. The most advanced spacecraft would not be engines that move a ship through the cosmos. They would be devices that move the cosmos around the ship. Think of spacetime not as an empty stage, but as a stretchy fabric. If you could contract that fabric in front of your vessel, you would not be moving toward your destination. Your destination would be pulled closer to you. Simultaneously, if you expanded the fabric behind you, the space you leave behind would stretch outward, pushing you forward from the rear. In this scenario, the ship itself is caught in a smooth, unmoving bubble of normal space. It experiences no acceleration forces, no G-forces pinning the crew to their seats. It is simply standing still while the universe dramatically rearranges itself. The concept of movement, of traveling from point A to point B, becomes an illusion. You arrive without having gone anywhere. This is not just a new engine, it is a new relationship with reality, transforming us from passengers on a vast and unforgiving cosmic ocean into potential masters of its very currents. The ocean itself is what moves the surfer forward, a perfect analogy for the first true principle of this new propulsion. This is the realm of the Alcubierre drive, a concept that turns the surfer's wave into a ripple in the fabric of spacetime. Proposed by physicist Miguel Alcubierre, this theoretical framework suggests a spacecraft could nestle inside a bubble of flat, normal space. The magic happens not to the ship, but to the universe immediately around it. Spacetime in front of the vessel is dramatically compressed, pulling the destination closer. Simultaneously, spacetime behind the vessel is radically expanded, pushing the point of origin further away. The ship inside this warp bubble is simply carried along, a stationary passenger on a moving sidewalk made of reality itself. You are not moving faster than light through space. You are moving while space itself is manipulated around you. This sidesteps the cosmic speed limit because the bubble and its contents are not undergoing local acceleration. Dr. Harold Sonny White, a leading researcher at the Limitless Space Institute, describes the ongoing work to bring this from equations to reality. His team is exploring the creation of microscopic warp fields in laboratory settings, searching for the faintest signature that spacetime can be intentionally bent in this way. The key to creating this warp bubble lies in a strange and exotic requirement: negative energy. Think of positive energy as what makes spacetime curve in a way that creates gravity, like a bowling ball on a trampoline. Negative energy would be the opposite, creating a kind of anti-gravity effect that warps spacetime in the reverse direction. One potential source for this exotic requirement is a well-documented quantum phenomenon called the Casimir effect. When two perfectly smooth, uncharged metal plates are placed extremely close together in a vacuum, they are pushed together by a mysterious force. This happens because the space between the plates excludes certain quantum fluctuations, effectively creating a region with lower energy than the surrounding space, a form of negative energy density. While the amounts generated are infinitesimally small, it provides a physical precedent that such effects are real. This principle redefines our idea of motion. Your coordinate velocity, your speed through the backdrop of the universe, could be phenomenal, while your proper velocity, your speed relative to the space immediately around you, remains zero. You would experience no time dilation, no crushing g-forces. Causality, the rule that cause must precede effect, remains intact from your perspective inside the bubble. It is like running on a treadmill. You are moving your legs, but the moving belt keeps you in the same spot relative to the room. Now, imagine the entire gym floor is the moving belt, and you are just standing still. This is not merely a new way to travel. It is a demonstration that motion itself is relative when you hold the threads of spacetime in your hands. That idea of a moving sidewalk made of reality leads directly to the second revolutionary principle. Think of a marble resting on a taut, flexible rubber sheet. You do not push the marble to make it move. Instead, you press your finger into the sheet ahead of the marble, creating a dip. The marble naturally rolls downward into that new depression you have created. This is the essence of local gravity manipulation, the art of creating artificial gravity wells to pull a spacecraft forward. Rather than pushing the ship, you reshape the spacetime in front of it, compelling the vessel to fall endlessly toward a destination of your own making. The legendary physicist Kip Thorne helped illuminate how such manipulations are not magic, but a direct consequence of Einstein's general relativity. In his view, mass and energy tell spacetime how to curve, and that curvature is what we perceive as gravity. A planet creates a deep well in the cosmic fabric, and we orbit it like a marble rolling around a funnel. The most advanced spacecraft would not just ride these existing curves, they would generate their own. The technology to do this remains hypothetical, centered on the concept of a gravity generator. Such a device would not create gravity by spinning a ship to produce centrifugal force, a mere simulation of gravity through acceleration. A true gravity generator would use concentrated energy, or perhaps exotic forms of matter, to create a genuine curvature in spacetime itself. It would produce a real gravitational field, a true dip in the fabric of the universe, on demand and in any direction. Imagine a spacecraft needing to travel to a distant star. Instead of igniting its engines, it activates a powerful gravity generator, projecting a focused, intense gravity well thousands of kilometers ahead of its path. The ship is not pulled by this well in the traditional sense of a rope. Instead, the space between the ship and the artificial well becomes sloped, like a hill starting just outside the ship's hull. The vessel simply begins to slide down this manufactured spacetime gradient, accelerating smoothly and effortlessly. For a truly breathtaking case study, consider a spacecraft creating a microscopic, artificial black hole directly in front of it. The ship is not in danger of being crushed, as the black hole is not a massive, star-sized object, but a tiny, controlled point of immense density. Its gravitational pull over a short distance would be incredibly powerful, creating an extraordinarily steep slope in spacetime. The spacecraft would then slide down this precipitous gradient, achieving immense apparent speed without ever firing a thruster. This is the promise of inertialess travel. Since the ship is in a state of perpetual freefall into a gravity well it creates itself, the crew inside would feel no acceleration forces. There would be no violent push into their seats, no risk of being turned to jelly by high G-forces. They would be weightless, comfortable, and stationary within their local frame of reference, even as their vessel plummets through the cosmos at a substantial fraction of light speed. Mastering gravity in this way is not just an improvement to propulsion, it is the key to redefining locomotion itself. We stop being objects that move through space and become architects who shape the very geometry of the journey. The quantum vacuum is not an empty void. It is a seething, bubbling sea of energy, alive with particles that flicker in and out of existence in a heartbeat. This is the third principle, quantum vacuum engineering, where a spacecraft stops carrying fuel and starts harvesting power from the universe itself. Think of the void of space not as nothing, but as a reservoir of unimaginable power, a resource we are only beginning to learn how to tap. The physicist Casimir provided the first tangible clue that this energy could be manipulated. He predicted that if you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they would be pushed toward each other by an invisible force. This happens because the narrow gap between the plates excludes some of the longer wavelength quantum fluctuations. The energy density outside the plates becomes greater than the energy density inside, creating a pressure differential that forces the plates together. This Casimir effect is not just a theoretical curiosity. It has been measured in laboratories, proving that we can indeed exert force by manipulating the quantum foam of empty space. Now scale this idea up to a cosmic level. A futuristic spacecraft would not need to expel its own propellant. Instead, it could use vast, complex structures to create a similar pressure differential against the quantum vacuum itself. It would be pushing against the fabric of spacetime, using the universe's own inherent energy as its reaction mass. One theoretical framework for achieving this is the Schwinger effect, which describes how a sufficiently powerful electric field can rip particle and antiparticle pairs directly out of the quantum vacuum. While creating such fields for propulsion is far beyond our current abilities, it points toward a future where we don't just push against the vacuum, but actively pull propellant from it. Imagine a ship with vast, shimmering quantum sails. These are not sails to catch sunlight, but intricate grids designed to interact with the ceaseless dance of virtual particles. By carefully controlling the energy states across these sails, the ship could create a region of higher quantum pressure on one side and lower pressure on the other. It would be like a sailboat setting its sails to catch the wind, only here the wind is the fundamental energy of reality. The ship would be propelled forward, pushed by the restless energy of empty space. The challenge, of course, is monumental. Extracting usable, net positive energy from the zero-point field is one of the greatest hurdles in theoretical physics. The energy is there, but it is chaotic and fleeting, like trying to harness the power of 1,000,000 microscopic lightning bolts all striking at once. Yet, the principle stands as a profound revelation. The emptiness we once thought was a barrier to travel is in fact the very medium that could carry us. We stop seeing space as a void to be crossed and start recognizing it as an ocean, full of currents and energy, waiting for us to learn how to sail. A magician snaps a tablecloth from a fully set table, and the plates and glasses remain perfectly, impossibly still. This classic illusion holds the key to the fourth principle of advanced spacecraft. They do not fight inertia, they cancel it. Imagine accelerating to near light speed in an instant, or making a 90-degree turn at a velocity that should turn a ship and its crew into a molecular smear, yet feeling absolutely nothing. This is the promise of inertial cancellation, a technology that would allow a vessel to change its velocity without experiencing the inertial consequences described by Newton. For centuries, we have accepted inertia as a fundamental property of matter. Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. When you accelerate your car, you are pushed back into your seat. When a rocket ignites its engines, the astronauts are pressed into their couches. This resistance to changes in motion is inertia, and it has always been an unbreakable rule. But what if inertia itself is not a fixed, intrinsic property? Physicist James Woodward has proposed a radical idea. He suggests that inertia is not something an object possesses on its own, but a gravitational effect, a kind of pushback from the rest of the mass in the universe. This concept, rooted in Mach's principle, implies that inertia is a dynamic interaction, not a static property. Woodward's Mach effect thruster is an attempt to test this. It uses piezoelectric crystals to oscillate masses back and forth at high frequencies. The theory posits that during these precise oscillations, the mass of the object fluctuates ever so slightly. By pushing during the brief instants when the mass is higher and pulling back when it is lower, the device could, in theory, generate a net thrust without expelling any reaction mass whatsoever. It would be pushing against the fabric of spacetime itself, manipulating its own inertial properties to create motion. This connects to a deeper layer of physics, the Higgs field. You can think of the Higgs field as an invisible, treacly medium that fills all of space. Particles interacting with this field acquire mass, and with mass comes inertia. The dream of inertia control is the ability to locally alter how an object interacts with this field, effectively turning its mass and inertia up or down like a dial. A spacecraft equipped with such technology would be unshackled from the laws of motion as we know them. Picture a vessel approaching a binary star system at a substantial fraction of light speed. A navigational hazard appears, an asteroid field blocking its path. In any conventional ship, attempting a sharp turn at such velocity would generate g-forces millions of times greater than Earth's gravity, instantly crushing the ship into oblivion. But this ship simply activates its inertial cancellation system. To an outside observer, it veers at a right angle with impossible agility. Inside, the crew feels nothing. A cup of coffee sitting on a console does not slide or spill. The ship and everything within it has become, in a local sense, divorced from the universe's resistance to acceleration. It has defied the foundational rule that every action has an equal and opposite reaction, not by breaking the rule, but by redefining the very nature of the action. A spinning top in a thick fluid does not simply turn in place. It drags the very liquid around it into a slow, swirling dance. In the same way, a massive rotating object does not just sit within spacetime. It twists the fabric of reality around itself, a phenomenon known as frame dragging. This is the fifth principle, a propulsion method that uses the Lense-Thirring effect to screw a vessel through the cosmos. Predicted by Einstein's theory of general relativity, this effect states that any rotating mass will pull spacetime into a vortex around it. it is not just a theoretical idea. Astronomers have observed this exact phenomenon around rapidly spinning neutron stars, the cosmic powerhouses known as pulsars. As these ultra-dense stellar corpses rotate, they drag the fabric of spacetime along with them, creating a measurable distortion that confirms our universe is not a rigid background, but a malleable fluid. How could a spacecraft harness this cosmic whirlpool? Imagine a vessel equipped with a massive ring, a cylinder constructed not of ordinary metal, but of some ultra-dense material, perhaps degenerate matter similar to what is found in a white dwarf star. This ring is set into a furious, hyper-rapid spin. According to the Lense-Thirring effect, this rotation would generate a frame-dragging field, a localized vortex in spacetime that twists the empty void around the ship. The vessel would not be pushing against anything. Instead, it would be caught in its own self-generated current, pulled forward along its axis of rotation as if spacetime itself were a screw and the ship was the thread being drawn through it. The engineering challenges are almost beyond comprehension. Creating and containing a cylinder of such density and spinning it to the required speeds without it flying apart would demand material science we can scarcely dream of. Yet the principle reveals a profound truth. Rotation is not merely for stability or artificial gravity. For an advanced civilization, spin could be the engine. It transforms a simple turn into a direct engagement with the geometry of the universe, allowing a ship to navigate not by moving through space, but by persuading space to move it. Gravity is a force that pulls, but what if you could create a substance that pushes? This is the strange promise of exotic matter, a hypothetical material with properties that turn common sense on its head. Where normal matter has positive energy density and attracts, exotic matter would possess negative energy density, creating a kind of gravitational repulsion. It sounds like science fiction, yet it emerges as the indispensable ingredient for almost every concept of advanced propulsion. Without it, a stable warp bubble would collapse instantly, and a traversable wormhole would snap shut. Theoretical physicist Lawrence Krauss has often highlighted the profound implications of such a material. He points out that negative energy is not forbidden by our current laws of physics, but its existence on a usable scale would challenge our deepest understanding of cause and effect. The very stability of spacetime, as described by Einstein's equations, relies on certain energy conditions being met. These are rules that say, in essence, that energy density must be positive and that gravity must always be an attractive force. Exotic matter, by its very definition, violates these conditions. It breaks the rules that keep reality rigid and predictable. The most famous of these is the null energy condition, a cornerstone of general relativity that exotic matter would simply ignore. This is not a minor loophole, it is a fundamental rewriting of the cosmic rulebook, allowing for geometries of spacetime that are otherwise impossible. So where could we even hope to find such a substance? The most promising candidate comes from a quantum effect we have already observed. The Casimir vacuum, the space between two closely placed plates, is not truly empty. It has a lower energy density than the surrounding space, effectively creating a tiny region of negative pressure. This is a real, measurable instance of the kind of exotic effect we would need, though the amounts of energy involved are vanishingly small. Beyond this, physicists speculate about other potential sources, like certain configurations of quantum fields or the strange state of matter inside a black hole's event horizon. These are all theoretical, pointing to a deeper layer of physics where the concepts of positive and negative are more fluid than we once believed. Now, picture a breakthrough in a heavily shielded laboratory. After decades of work, a team of researchers manages to stabilize a field of negative energy no larger than a grape. It flickers into existence for a mere fraction of a second, but its instruments confirm the impossible, a region of space where the energy density is definitively, measurably less than zero. This microscopic success would be a thunderous proof of concept, demonstrating that the physics allowing for exotic matter is real. Scaling that up to the amounts needed to warp a bubble of spacetime large enough for a spacecraft is a challenge of another magnitude entirely, one that might require technologies we cannot yet conceive. The materials needed to build these ultimate spacecraft are not stronger alloys or more efficient engines. They are substances that manipulate the fundamental fabric of cause and effect, materials as strange and powerful as the physics they are meant to command. Architects of a warp drive do not design an engine, they draft the specifications for a temporary fault in reality. Their blueprint details a precise pocket of flat spacetime, a safe harbor for the ship, encased within a furious ring of distorted physics. This ring is the active component, a torus of exotic energy that must maintain a perfect balance, compressing the universe ahead while expanding it behind. The shape of this energy distribution is not arbitrary. It must form a specific negative energy density profile, a mathematical curve that prevents the bubble from collapsing under its own gravitational stress or tearing itself apart in a violent instability. Inside a lab at NASA Eagleworks, researchers are not building starships. They are using sensitive instruments to detect the faintest whisper of a warp field signature. Their experiments aim to measure a microscopic shift in the path of a laser beam as it passes through a region where spacetime has been subtly manipulated, searching for proof that the equations can manifest in our world. The core of this system is the warp field generator, a device that must orchestrate immense forces. It would likely be a massive structure, a ring of exotic matter, or a complex array of capacitors and field emitters surrounding the vessel's midsection. This generator works in concert with a field sustainer, a network of stabilizers that constantly monitor and correct the warp bubble's geometry, preventing it from oscillating or decaying. The most mind-bending component is the navigation system. This is not a system that plots a course through space, but one that calculates how to reshape spacetime itself. It must solve Einstein's field equations in real time, determining exactly how to warp the local cosmos to pull the destination closer and push the origin away, all while ensuring the bubble's interior remains perfectly calm. The materials for such a craft are as exotic as the physics. The generator ring must withstand spacetime curvatures so extreme they would shred ordinary matter, requiring alloys stabilized by powerful electromagnetic fields or perhaps materials woven from condensed energy states. The power demand is equally staggering. Containing and shaping a warp bubble could require energies on par with the total output of a star, pointing to power sources like matter-antimatter annihilation or the direct harnessing of zero-point energy. Before any physical construction, engineers run computational models that simulate the entire process. They input the desired effective velocity, and the software calculates the necessary adjustments to the local spacetime metrics. The simulation shows the grid of space contracting into a deep blue well in front of the virtual ship, while expanding into a stretched red plane behind it. The ship's icon on the screen remains motionless, its coordinates changing not because it moves, but because the simulated universe is flowing around it. This is the critical juncture where abstract principle confronts concrete engineering, transforming a beautiful mathematical possibility into a set of brutal technical problems waiting for solutions. A single gram of fuel could power an entire city for centuries. This is the staggering energy density required to command the fabric of spacetime. the original calculations for the Alcubierre drive were sobering. They suggested you would need to harness the equivalent of Jupiter's entire mass converted directly into pure energy just to form a single warp bubble. Such a figure placed the concept firmly in the realm of fantasy, yet more recent and optimistic research has dramatically lowered that barrier. Refinements in the proposed geometry of the warp bubble itself suggest the energy requirement could be reduced to something akin to the mass of a small spacecraft, a monumental challenge still, but one that no longer defies all reason. Dr. Richard Obersey, a physicist deeply involved in these concepts, often speaks of scaling laws. He suggests that as we develop a better understanding of quantum gravity, we may discover techniques to lower the energy barrier even further, perhaps by orders of magnitude. The key is not finding more power, but learning how to use it with unimaginable precision. So where could such power possibly come from? The first step beyond our current nuclear fission might be fusion, the process that powers the stars. A stable fusion reactor could provide a steady, immense flow of energy, but even this may only be a starting point, sufficient perhaps for early experiments in microwarps, but not for a full-sized starship. To go further, we must look to more extreme sources. Imagine a black hole engine. This would utilize the Penrose process, a method to extract rotational energy from a spinning black hole. A spacecraft could, in theory, feed matter into the black hole's ergosphere, the region just outside its event horizon, and collect the tremendous energy released. It would be like dropping a log into a cosmic whirlpool and capturing the resulting splash of power. Even more speculative is the idea of direct vacuum energy extraction, tapping the seething zero-point field we discussed earlier. This would be the ultimate power source, drawing fuel from the empty space that surrounds the ship, turning the void itself into a boundless reservoir. Consider an illustrative scenario. A starship approaches a vibrant young star. It does not orbit at a safe distance. Instead, it plunges into the star's corona, a tempestuous outer atmosphere of superheated plasma. Vast magnetic field generators on the ship's hull act like dynamos, harvesting the star's raw, turbulent energy and converting it into a stable, usable form. This harvested power is then channeled to the warp field generators, fueling the next leap across the light years. Or, for a more contained approach, envision the ship creating its own power source. It uses immense energy to forge a microscopic, artificial singularity, a black hole no larger than an atom. Contained within a powerful magnetic bottle, this singularity would emit Hawking radiation, a steady stream of energy that the ship could collect. This micro-singularity would be the ultimate battery, a captive piece of cosmic power that slowly evaporates, providing energy for the journey. The deep dive into energetics reveals a fundamental truth. The fuel for these ships is not gasoline or hydrogen. It is the manipulation of gravity itself, the direct conversion of mass into space-time curvature, the harvesting of quantum fluctuations. The power source is not a separate component. It is the very art of commanding the fundamental forces of the universe. We are not just building a bigger engine, we are learning to write the rules of the cosmic game. The starfield outside your viewport is a lie. When your ship reshapes local spacetime, the light from distant stars bends and warps, making traditional celestial navigation utterly useless. You are no longer a ship sailing on an ocean. You are a force that bends the ocean floor, and you need a map of the depths, not the surface. Piloting such a vessel requires a navigation system that reads the curvature of spacetime itself, interpreting the invisible topography your ship creates. Astrodynamicists working on this problem point to a new class of sensor, devices that measure the local metric tensor. This is not a device that sees light. It is an instrument that feels the fundamental geometry of the universe, detecting the subtle hills and valleys in the fabric of reality that your ship's warp field generates. These sensors would feed a torrent of raw data into a navigation computer, a system tasked with an almost divine calculation. It must solve Einstein's complex field equations in real time, constantly adjusting the warp bubble's shape and strength to make minute course corrections. A slight overcompression of spacetime ahead could send you veering wildly off course, while an instability in the expansion behind you might create a dangerous drag effect. The computational power required is staggering, demanding quantum processors that can model the fluid dynamics of spacetime itself. Every minor adjustment carries profound risks. An imperfectly formed warp bubble could radiate gravitational waves, rippling out across the solar system with unpredictable consequences. A miscalculation near a planet could inadvertently create tidal forces, shaking its crust or disturbing its atmosphere. This necessitates the development of strict protocols for safe spacetime travel, cosmic speed limits, and right-of-way rules for vessels that do not technically move. Imagine the ship's AI pilot, a silent intelligence processing the live feed from its quantum gravity sensors. It is not looking for asteroids or other ships. It is reading the spacetime landscape, searching for potential hazards. It identifies a region ahead where the natural curvature of spacetime is too steep, a gravity well from a hidden dwarf star that could interact catastrophically with the ship's own artificial well. The AI makes a nanosecond decision, subtly reshaping the forward warp field to skirt the danger zone, navigating the ship through a safe pass in the invisible mountains of gravity. Steering is no longer about turning a wheel. It is about recalibrating the universe. The pilot's role transforms from a driver into a cosmic cartographer, charting a course not through space, but through the very forces that define it. The human body evolved for a world with fixed rules. Gravity pulls down, time flows forward at a steady pace, and motion comes with a predictable physical sensation. Inside these advanced vessels, every one of those rules becomes a variable. The ship itself is a sanctuary of normal physics, but the act of its travel manipulates the environment in ways our biology was never designed to endure. Space medicine experts like Dr. Anya Sharma warn that the greatest threat to an interstellar mission may not be the vacuum of space, but the physiological consequences of riding a warp in reality. The crew is not just traveling, they are living inside a machine that actively bends the cosmos. The most immediate challenge is the potential for sensory conflict. Your eyes, looking at a static viewport display, show a star field that is shifting and distorting due to gravitational lensing. Your inner ear, however, feels no acceleration, no tilt, no movement whatsoever. This complete disconnect between what you see and what you feel is a recipe for profound and debilitating disorientation. The brain struggles to reconcile the data, potentially leading to a kind of cosmic vertigo, chronic nausea, and a deep psychological unease. You are surrounded by the visual proof of immense speed, yet your body insists you are standing still. How do you trust your own senses when the universe itself is being untrustworthy? Then there is the specter of variable time dilation. While the warp bubble's interior is designed to be a protected frame, rapid adjustments to the spacetime metric could create fleeting, localized time slips. Picture a crew member, an engineer named Lena, conducting a routine systems check in a service corridor. The ship performs a sudden, automated course correction, recalibrating the warp field to avoid a dense cloud of interstellar dust. For a few milliseconds, the local spacetime geometry around her station fluctuates. From her perspective, the rest of the ship seems to stutter, her colleagues moving in a jerky, stop-motion blur. She experiences a wave of temporal nausea, a feeling of being unstuck from the flow of time itself. The effect passes as the field stabilizes, but the psychological imprint remains. How do you prepare a human mind for the possibility that time itself may not be a constant river? Long-term exposure to high-energy field gradients presents another unknown. Even with perfect shielding, the crew would be living mere meters from a torus of exotic energy capable of warping the vacuum. The residual effects, what Dr. Sharma calls field bleed, could have cellular and genetic consequences we cannot yet predict. It might accelerate aging in certain tissues or subtly alter neural conductivity or affect the very structure of DNA. The environment inside the ship is not merely a habitat, it is a biological experiment. The solutions are as radical as the problems. Inertial damping fields would need to do more than just cancel G-forces. They would have to actively stabilize the crew's sensory systems, providing a synthetic frame of reference to prevent disorientation. For high-energy maneuvers or field transitions, biological stasis might be necessary, placing the crew in a suspended animation where their metabolic processes are paused, shielding them from temporal and physiological stresses they cannot consciously perceive. Ultimately, the human form itself may need to adapt. Genetic therapies could harden our cells against field radiation, while cybernetic enhancements could provide direct neural interfaces with the ship's navigation system, allowing a pilot to feel the curvature of spacetime as intuitively as we feel balance. The final frontier is not just outside the ship, it is within us. Mastering the physics of spacetime is only half the journey. The other half is redesigning the ancient, fragile vessel of the human body to survive the voyage. That quiet hum you hear is not an engine, but the sound of the ship holding itself together against the impossible. The hull of such a vessel is not a passive shell. It is an active participant in a constant dialogue with a warping universe. It must be built from materials that do not just endure stress, but redefine what stress even means. The forces at play are not mere pressure or heat, but fundamental threats to the cohesion of matter itself. Extreme tidal forces at the warp bubble's boundary would try to pull a single atom in 3 different directions at once, spaghettifying any ordinary metal. The quantum vacuum just outside the hull is a seething maelstrom of virtual particles, and a structural flaw could trigger a localized vacuum decay, a catastrophic bubble of true nothingness that would eat through the ship like a hole in reality. The material must remain stable when the very concepts of here and now are in flux. Dr. Kenji Tanaka, a materials scientist working on metamaterials, explains that we are moving beyond the periodic table. The elements we know are simply not up to the task. We need to engineer substances with properties not found in nature, creating meta-stable lattices that can withstand gravitational shear forces that would tear neutron star crusts apart. One candidate is a form of metastable metallic hydrogen. Under immense pressures like those found at Jupiter's core, hydrogen is predicted to become a solid metal, a superconductor with incredible strength. The trick is crafting it in a way that it remains in that state even at room temperature and pressure, creating a lattice of protons with no electrons in the way, a perfect, ultra-dense shield. Another possibility involves weaving carbon nanotubes with topological insulators. The nanotubes provide a backbone of legendary tensile strength, while the topological insulators have a bizarre quantum property. Their interiors are insulators, but their surfaces are perfect conductors. This creates a skin for the ship that is immune to external energy fluctuations, a material that can literally shrug off the violent particle storms generated by the warp field. Manufacturing such a composite is a challenge that might only be possible in the pristine environment of space. In zero gravity, without the distortions of a planetary pull, nanofabricators could slowly assemble these materials atom by atom, layer by layer, in orbital forges. We might use self-assembling smart materials programmed with the blueprints of their own structure, which flow into place like a liquid and then lock into a solid more durable than diamond. Picture a section of the ship's inner hull. It is not a single sheet of metal, but a dynamic composite that looks almost organic. As the warp field engages and the space-time curvature around the ship intensifies, the material responds. Its atomic bonds, influenced by embedded quantum dots, subtly shift their resonance to match the frequency of the local spacetime geometry. It is not fighting the bending of space, it is harmonizing with it. The hull bends because space bends, maintaining its structural integrity by becoming one with the distorted fabric of the universe. This active alignment prevents any internal stress from building up, allowing the ship to survive journeys that should, by all known physics, vaporize it. The vessel itself is a masterpiece of material science, a symphony of engineered atoms playing in tune with the cosmos. Without a hull that can dance with space-time, the most powerful warp drive is nothing more than a theoretical bomb. The silent intelligence at the heart of such a vessel faces a task of almost mythical proportions. It must command a force that bends the universe, and to do so, it must predict how the universe will bend in return. This requires a computer that does not just calculate, but one that simulates reality itself, solving the deepest laws of physics in the blink of an eye. The computational demand is not just high, it is astronomical. To control a warp field, the system must continuously solve Einstein's field equations, a set of immensely complex formulas that describe how mass and energy curve spacetime. Doing this in real time for the dynamic and violent distortions the ship creates is a problem that would freeze any supercomputer we have today. Quantum physicist Seth Lloyd puts it in stark terms. He explains that the amount of information processing required to manipulate a region of spacetime is directly related to the energy involved. To control a star's worth of power, you need a processor that can handle a correspondingly cosmic amount of information. This is the realm of quantum computing, where bits are not just ones or zeros but can exist in multiple states simultaneously. A quantum computer could, in theory, model the probabilistic, fluid nature of spacetime geometry in a way that classical computers simply cannot. But we may need to look even further. Some theorists speculate about biocomputers, vast crystalline or neural networks that use complex biological processes for analog computation, or even more exotic ideas like spacetime itself becoming the processor. Imagine a gravity wave processor where the very ripples in the fabric of the universe, the distortions the ship creates, are used to perform calculations. The warp field would not just be an effect of the computer's work, it would be an integral part of the computer itself. The algorithms running on this system are as specialized as the hardware. They are predictive modeling routines that must forecast how a minor adjustment to the forward compression field will affect the stability of the entire bubble seconds later. They are error correction codes that constantly scan for microscopic flaws in the spacetime metric, tiny tears or weak spots that could escalate into a catastrophic failure. Machine learning networks would be trained on countless simulations, learning to recognize the precursor signatures of a bubble collapse and instinctively applying the correct countermeasures. Picture the ship's navigation core during a routine transit. It is not merely holding a course, it is running a perfect, continuous digital twin of its own warp bubble. This simulation updates millions of times per second, a perfect mirror of reality. The system detects a subtle harmonic resonance building in the portside expansion field. Instantly, it cross-references this with its predictive models and recognizes a 97% probability of a metric oscillation within 3.2 seconds. Without human intervention, it instructs the field sustainers to make a nanoscopic power shift, altering the geometry of the bubble by a factor so small it is meaningless on any human scale. The resonance dampens and vanishes, the entire event is logged, and the machine learning model is updated, making the system slightly smarter for the next time. This is not navigation, it is a constant, high-stakes negotiation with the fundamental laws of physics. The brain of the ship must possess an understanding of the cosmos so deep and intuitive that it can dance with reality, leading it in a carefully choreographed performance where a single misstep means oblivion. This quiet power to reshape the cosmos carries a burden heavier than any star. We are no longer just inhabitants of a universe with fixed laws. We are becoming its editors with the ability to rewrite the rules of reality, even for a moment. This is not merely a technological leap. It is a philosophical earthquake that forces us to ask, what is our responsibility when we can play with the fabric of existence? The potential for misuse is as vast as the power itself. Imagine a weapon that does not explode, but creates a microscopic, artificial black hole in the heart of a city. It would be an unstoppable gravitational sinkhole, devouring everything in its path. Or consider the terrifying possibility of a cascading spacetime instability, a warp bubble collapse that radiates gravitational shockwaves, accidentally altering the orbits of planets in a solar system light years away. Power to move a planet also means the power to unwittingly destroy one. Philosophers like Dr. Aris Thorne warn of the cosmic prime directive dilemma. If a less advanced civilization developed on a world we could easily manipulate, do we have the right to move an asteroid threatening them, even to save them? Such an act, however benevolent, would be indistinguishable from divine intervention, fundamentally altering their worldview and their technological trajectory. It introduces a paternalistic dynamic on a galactic scale, where we become the guardians of species who never asked for our help. This technology transforms our identity. For all of human history, we have been characters in a story written by physics. Now we are picking up the pen. We are transitioning from inhabitants to co-authors of the cosmos. What happens to our sense of purpose when the stage itself becomes a prop we can rearrange? The questions become even more profound when we consider the ultimate act of creation. Could this mastery of spacetime lead to the ability to forge new universes, or at least stable pocket dimensions? If so, what are the moral implications of creating a cosmos, even a small one? Are we responsible for the life that might eventually evolve within it? Do we have a duty to be a benevolent God, or do we simply flip the switch and walk away? Consider a stark dilemma. A massive asteroid is on a collision course with an inhabited world. With spacetime manipulation, you have two choices. You could move the asteroid, a relatively simple act of celestial mechanics. Or you could move the planet itself, shifting its entire orbit to a safer position. The first option treats the planet as the fixed center of the drama. The second option treats the planet as a marble to be flicked across the solar system. The technological difference might be minor, but the philosophical chasm between them is immense. One preserves the world's place in the cosmos, the other asserts our dominion over it. This is the ultimate test of our maturity. The power to command local physics does not just demand better engineers, it demands wiser beings. It forces us to confront our role not as masters of the universe, but as its newly conscious stewards, holding a power we are only beginning to understand how to wield without breaking everything we touch. The price of a ticket to Mars could soon rival the cost of a flight from New York to London. This is not a distant dream, but the logical conclusion of a technology that makes distance irrelevant. The very concept of an aerospace industry, built on the immense cost and complexity of fighting gravity and crossing voids with reaction mass, would vanish almost overnight. In its place, a new industrial revolution would bloom, centered on spacetime engineering, the synthesis of exotic matter, and the construction of gravity generators. We would stop building rockets and start forging the architecture of reality itself. Economists modeling this shift speak of a potential post-scarcity economy. When the entire galaxy becomes your backyard, resources are no longer scarce. A single metallic asteroid, towed into Earth orbit by a tug that reshapes spacetime around it, could contain more iron, nickel, and platinum group metals than have been mined in all of human history. The energy from 1,000 suns, harvested by fleets of automated vessels, could power our civilization for millennia. The fundamental drivers of conflict and economy, the struggle for resources and energy, could simply dissolve. This new abundance would not arrive without profound geopolitical tremors. The old map of terrestrial power, defined by nations and borders, would be rendered obsolete. What happens when the first corporation or nation-state claims an entire Earth-like exoplanet for itself? Could we see a new era of conflict, not over oil fields, but over the gravitational anomalies needed to power warp drives, or over systems rich in the exotic materials required for their construction? The very nature of law would have to expand into the void. We would need interstellar governance, a set of rules for right-of-way between warp-capable vessels, and protocols for first contact that prevent a simple trade mission from appearing as an act of God-like intervention. On a human scale, daily life would transform in ways we can barely comprehend. Picture a family living in a domed city on Europa. The parent works as a quantum ecologist, managing the biosphere of a terrarium on a world orbiting a star in the Orion Arm. Their commute is not a drive through traffic, but a scheduled warp jump to an office complex floating in the alien system's void. They are home for dinner every night, their journey across light years as routine and unremarkable as a subway ride is today. This fluid movement would lead to an unprecedented fusion of cultures, both human and potentially alien. Isolated colonies would develop their own unique arts, philosophies, and social structures, creating a tapestry of human experience far more diverse than anything on Earth. And if we were to discover other intelligent life, this technology would force a meeting of equals. We would not arrive in primitive ships, having struggled for generations to cross the Gulf. We would step out of a bubble of curved space, demonstrating a mastery of the cosmos that commands a fundamental respect. The ripple effects of this single technology would not just change how we travel, they would redefine what it means to be a civilization, scattering humanity across the stars and forcing us to grow into our new role as citizens of the galaxy. The silent hum of a warp drive is a sound the universe has never heard before, and we must ask what echo it leaves behind. Every time we compress spacetime ahead of a ship and stretch it behind, we are creating a ripple, a gravitational wave that propagates outward across light years. While a single journey might be a whisper, a future filled with thousands of such vessels could create a persistent, low-level gravitational radiation background, a new form of cosmic noise. This is not pollution in the terrestrial sense, but a fundamental alteration of the cosmic environment. The vacuum of space is not truly empty, it possesses a specific, stable energy state. Cosmologists worry that repeated, violent manipulations of local spacetime could, in theory, nudge a region of space into a different, lower energy state. This process, called vacuum decay, would be the ultimate ecological catastrophe. A bubble of this new, stable vacuum would expand at the speed of light, rewriting the fundamental laws of physics as it grows and erasing the universe as we know it. While the probability is considered infinitesimally small, the stakes are literally infinite, forcing a level of caution we have never before had to contemplate. This leads to the concept of a spacetime pollution metric, a way to measure the cumulative stress our travels inflict upon the cosmic fabric. Just as we monitor carbon emissions, future interstellar agencies might track gravitational wave output and vacuum stability indices for every warp transit. Certain regions of space may be too delicate for this kind of travel. Imagine a complex, beautiful nebula where new stars are being born. Its structure is held in a delicate balance by subtle gravitational and magnetic fields. The passage of a warp-capable ship through its heart could disrupt that equilibrium with unpredictable consequences, perhaps triggering premature stellar collapse or scattering the raw materials for future planetary systems. We might need to establish permanent no-fly zones around such cosmic nurseries, treating them with the same reverence we afford a pristine wilderness on Earth. The consideration extends to life itself. We assume that life requires a planet, water, and sunlight. But what if life exists in forms we cannot conceive? Life that thrives in the complex geometry of a neutron star's magnetosphere or perceives the universe through subtle fluctuations in the spacetime metric itself. Our careless passage could be to them what a sonic boom is to a fragile ecosystem, a shattering intrusion that disrupts their very existence. As we gain the power to reshape our environment, our responsibility expands to encompass the entirety of the cosmic landscape, demanding we learn to travel not just efficiently, but gently. Our search for intelligent life might be looking for the wrong things entirely. For decades, projects searching for extraterrestrial intelligence have scanned the skies for radio signals or the fleeting laser pulses of communication. These methods assume that other civilizations would announce their presence with a beacon, or that their technology would leak telltale signs like the radio chatter and rocket exhaust of our own industrial age. But if a society has mastered the art of moving space rather than moving through it, those signs would simply not exist. There would be no roaring engines, no fiery plumes of plasma, no expansive radio broadcasts leaking into the void. Their presence would be as silent and as subtle as a shadow passing over the sun. Astronomer Jill Tarter, a pioneer in this field, has long advocated for expanding our search parameters. She suggests we must look for the astronomical equivalent of footprints, not voices. The evidence would not be in the electromagnetic spectrum, but in the geometry of spacetime itself. The first signature might be a strange, Cherenkov-like radiation from a warp bubble. Just as a particle moving faster than light through water emits a blue glow, a vessel warping spacetime might release a faint burst of Hawking radiation, a whisper of particles at the boundary of the warp field. Our telescopes would need to be tuned not to light, but to these exotic emissions. The second clue could be transient gravitational wave patterns. Our current observatories like LIGO are built to detect the colossal ripples from merging black holes and neutron stars. But what about a much smaller, sharper ripple, one that appears and vanishes in an instant, moving in a straight line across the galaxy? This would be the gravitational wake of a ship that does not move, a ripple on the cosmic pond from a stone that never touched the water. The most startling signature might be the sudden appearance of a craft with no deceleration track. Our physics dictates that any object approaching at relativistic speeds must bleed off that immense energy somehow. We would see a blazing trail of radiation as it slows down. A warp-driven ship, however, does not slow down. It simply disengages its field. One moment there is empty space. The next, a vessel is there, stationary relative to a star, having arrived without any visible journey. This leads to a profound and unsettling possibility, the zoo hypothesis. What if advanced civilizations are all around us, but using this space-time technology to remain perfectly hidden? They could warp the light around their vessels for perfect cloaking, or mask their presence by leaving no thermal or radiative signature to detect. They would be like ghosts in the cosmic machine, observing a universe that cannot perceive them. Their very method of travel provides the ultimate stealth, making them invisible to every instrument we have ever built. Now picture a future SETI program, a generation from now. It does not use a forest of radio dishes pointing at the stars. Instead, it operates a global network of quantum gravity sensors, devices buried deep underground to shield them from terrestrial noise. These sensors do not listen, they feel. They monitor the subtle fabric of the local solar system, waiting to feel the gentle tug of a space-time distortion passing by. They are not looking for a message. They are looking for the wake of a ship that does not move, the faintest impression of a finger gently pressing into the fabric of reality. To find others, we may need to stop listening for their voices and start feeling for the distortions they leave on the silent surface of space. The dream of traveling without moving is older than the rocket itself. Long before Einstein penned his equations, storytellers were already bending the rules of space. H.G. Wells, in his novel The Time Machine, sent his protagonist hurtling through the ages not by building a faster vehicle, but by manipulating the fourth dimension itself. He sat still while the universe rushed past him. Decades later, editors like John W. Campbell championed tales of space warps and hyperdrives in the pages of pulp science fiction magazines, planting a powerful seed in the public imagination. These were not just flights of fancy, they were the first crucial thought experiments. Historians of science often note this pattern, where fiction provides the vocabulary and the conceptual playground that real-world scientists later explore. The wild idea comes first, and rigorous investigation follows. The mathematical foundation arrived with Albert Einstein and his theory of general relativity in 1915. His field equations described a universe where space and time were not a fixed stage, but a dynamic fabric that could be curved and shaped by mass and energy. This was the crucial turning point, translating a science fiction trope into a set of solvable, if immensely difficult, equations. For decades, the idea remained a theoretical curiosity, often dismissed as impossible by the mainstream. The pivotal moment came in 1994, when physicist Miguel Alcubierre published a paper that changed the conversation. He asked a simple, profound question, inspired by watching the Starship Enterprise travel at warp speed on television. Was it physically possible? His paper demonstrated that within the framework of general relativity, a warp drive was not explicitly forbidden. It required exotic matter, but the math checked out. This opened a door. Researchers like Dr. Harold Sonny White at NASA began to explore not if it could be done, but how. The culture of physics itself had to evolve to accommodate such a radical idea. It required a community willing to entertain what seemed crazy, to follow the mathematics even when it led to conclusions that defied common sense. The story of the warp drive is a powerful reminder that the line between imagination and invention is not a wall, but a permeable membrane. Our most ambitious dreams of the future often begin as a sketch on a page, waiting for the equations to give them life. Deep underground, shielded from the vibrations of a living world, a laser beam travels down a vacuum chamber 1 kilometer long. Its purpose is to measure a shift smaller than the width of a single proton. This is the scale of ambition in laboratories like NASA Eagleworks, where the dream of warp drive is being tested not with Starship hulls, but with the most sensitive instruments ever built. The goal is not to build an engine, but to find a fingerprint, the faintest whisper of a space-time distortion that proves the mathematics of Alcubierre and others can manifest in our reality. Dr. Harold Sonny White, who leads this research, often describes their work as searching for the first ripple in a pond, hoping to prove the water can be moved. Their primary tool is an instrument called a White-Jude warp field interferometer. It splits a laser beam, sending one path through a region where they hope to create a microscopic warp effect, and another along a pristine reference path. If the fabric of space within the test region is even slightly compressed or expanded, the laser beam passing through it will be minutely delayed or advanced, creating an interference pattern that betrays the hidden manipulation. A positive result would not be a roaring warp core, but a subtle shift in a pattern of light, a ghost in the machine that would change everything. Parallel to this, teams across the globe are probing the quantum vacuum with new precision. In a laboratory in Germany, scientists use ultra-smooth, nano-fabricated plates to probe the Casimir effect at distances of mere nanometers. They are not just confirming the existence of negative energy density, they are learning how to control it, searching for ways to amplify the effect from a microscopic curiosity into a measurable force. The challenge is one of almost absurd scale. The negative energy densities we can currently create are trillions of times weaker than what a theoretical warp drive would require. Yet, each experiment that successfully manipulates a vacuum fluctuation or measures a thrust from a quantum vacuum plasma thruster is a brick laid in the foundation of a new physics. These thrusters, often called Q thrusters or radio frequency resonant cavity thrusters, are another controversial but active area of research. They claim to convert electrical power into thrust without expelling any propellant, potentially by interacting with the quantum vacuum's virtual particles. While the measured thrusts are tiny, on the order of micronewtons, the implication that we can push against the fabric of spacetime itself is what drives the research forward. The work is slow, meticulous, and often meets with skepticism. Success is measured in data points that take months to collect and must be scrutinized for any possible error. A single experiment might aim to detect a warp signature 1,000,000 times smaller than the experimental noise floor, a task like trying to hear a single leaf fall in the middle of a hurricane. But the researchers persist, driven by the knowledge that if they can prove just once that spacetime can be intentionally warped for propulsion in a lab, the universe will suddenly become a very different and much smaller place. A warp bubble capable of faster-than-light travel is also a time machine in disguise. This is not science fiction speculation, but a direct consequence of the mathematics behind the Alcubierre metric. Within the framework of general relativity, a ship moving faster than light could, in principle, travel on a closed time-like curve. This is a path through spacetime that loops back on itself, allowing an object to return to its own past. The very act of arriving before you left shatters the foundational principle of causality, the rule that cause must always precede effect. Philosopher of physics Tim Maudlin forces us to confront the stark implications. If you could go back and prevent your own journey, what then becomes of the journey itself? The universe would be caught in a logical paradox with no clear resolution, suggesting that nature may have built in safeguards to prevent such contradictions from ever occurring. One of these safeguards might be Hawking radiation. The intense energy at the boundaries of a warp bubble could spontaneously generate a storm of particles and antiparticles. This radiation would not just bombard the ship, it could bleed energy from the warp field itself, causing the bubble to destabilize and collapse before it ever reached faster-than-light velocities. The very physics that enables the warp might also guarantee its destruction. Then there is the horizon problem. From the perspective of someone inside the warp bubble, the outside universe becomes invisible and unreachable. The warped region of spacetime acts as an event horizon, just like the surface of a black hole. No information, no light, no command signal from outside can ever reach the crew inside. They would be flying completely blind, unable to navigate or adjust their course based on what lies ahead. They would be prisoners in a bubble of their own making, set on a predetermined path they can no longer alter. Perhaps the most fundamental roadblock is the unphysical nature of the requirements. The negative energy densities needed are not just rare, they might be impossible to assemble in the stable configurations the equations demand. It is possible that the universe possesses a kind of cosmic censorship, a set of unwritten laws that prevent the formation of these reality warping structures, no matter how clever our mathematics becomes. This leads to the terrifying concept of the warp drive bomb. The energy stored in a warp field is immense, and if that field were to collapse or be disrupted, all that energy would be released at once. The result would not be a simple explosion, but a catastrophic burst of high-energy particles and gravitational waves, potentially obliterating anything in the vicinity. The ultimate propulsion system could also be the ultimate doomsday weapon. Acknowledging these profound hurdles is not an admission of defeat. It is the essential, rigorous work that separates wishful thinking from honest scientific progress. Confronting paradoxes is how we test the limits of our theories and refine our understanding of what is truly possible in this universe. The blueprint for a spacetime engine is signed by 1,000 different hands. No single mind, no lone genius, no solitary field of science can hope to contain the knowledge required to build it. This endeavor demands a confluence of disciplines, a meeting of minds where the language of quantum gravity must be translated for the nanotechnologist, and the ethics of cosmic stewardship must inform the engineer's design. It is a project that shatters the old silos of specialization, forcing a new kind of collaboration into being. Leaders of interdisciplinary institutes often speak of the initial friction. A cosmologist thinks in terms of billions of years and galactic scales, while a molecular engineer operates at the level of individual atoms. Their timescales, their jargon, their very definitions of success are worlds apart. The first challenge is not technological but social, building a shared vocabulary and a common purpose. The reward for overcoming this is a cascade of breakthroughs. A discovery in quantum computing, a new algorithm that can model complex field equations, might suddenly unlock a stalled problem in warp field stability. A materials scientist developing a new metastable composite to resist gravitational shear could provide the very component that makes a laboratory warp signature detectable for the first time. Progress in one field becomes the key that turns the lock in another. The organizational structure for such a monumental effort cannot resemble a traditional corporate hierarchy. It must be modeled on big science projects like CERN or the ITER fusion reactor, vast international consortia where thousands of scientists and engineers collaborate for decades toward a single, defining goal. These are ecosystems of innovation where shared data and open communication are the lifeblood of progress. Imagine a virtual research environment, a shared digital space that is part design studio, part laboratory, and part conference hall. A cosmologist, represented by an avatar, points to a shimmering hologram of a warp bubble stress profile. A nanotechnologist, joining from a clean room on another continent, overlays the atomic lattice of a proposed hull material. An AI specialist then runs a real-time simulation, showing how the two interact under extreme tidal forces. They are not working in sequence, they are co-designing the component together, their expertise fused in a single creative act. This is how the spacecraft of the future will be conceived, not as a collection of parts but as an integrated whole, born from the collective and seamless genius of humanity. The vessel itself becomes a testament to our ability to unite, a physical symbol of what we can achieve when every branch of knowledge reaches for the stars together. A functional starship that reshapes space does not emerge from a single eureka, a moment, but from a century of persistent, layered breakthroughs. Charting a course from our current laboratories to the launch of such a vessel requires a timeline that is both visionary and grounded, a map for a journey we are only beginning to understand. The first phase, unfolding over the next 20 years, is the proof of concept. Right now, in labs like EagleWorks, the goal is not thrust but a signal. The paramount milestone here is the first uncontested laboratory demonstration of a stable micro-warp bubble. This would not be a machine you can see, but a distortion in a laser interferometer, a data point confirming that spacetime can be intentionally compressed and expanded on a microscopic scale. Alongside this, researchers must make progress in synthesizing and stabilizing exotic matter. We are not building fuel tanks yet. We are learning to create a single, stable thread of negative energy density that lasts for more than a fraction of a second. This phase is about moving the idea from the pages of physics journals into the empirical world of experimental data. Following a confirmed proof of concept, the next 20 to 50 years enter the experimental validation phase. The question shifts from if we can warp spacetime to how we can control it. This period would see the development of the first material capable of containing a field of exotic matter without being torn apart by the gravitational shear forces. It might be a dynamic metamaterial that actively resonates with the warp field, a fabric woven from principles we are only now discovering. Another critical milestone here is the creation of the first artificial intelligence capable of real-time metric computation. This AI would not need to be fully sentient, but it must be able to solve Einstein's field equations almost instantaneously, making the constant, microscopic adjustments needed to keep a warp bubble from collapsing. These are not engines, but the tools we must forge to even begin building one. The third phase, spanning 50 to 100 years from today, is where engineering supersedes pure science. This is the era of the engineering prototype. The milestones become physical and monumental. We would see the construction of the first integrated warp field generator, a device that combines a stable exotic matter ring with a powerful energy source and a metric computation AI. Its first test might warp a region of space no larger than a grapefruit, but it would prove all the core technologies can work in concert. The power source itself would be a landmark achievement, likely a compact fusion reactor, or perhaps an early prototype of a quantum vacuum energy extractor. This phase is defined by scaling up, moving from tabletop effects to structures large enough to envelop a small probe. The final phase, a century or more in the future, culminates in the operational vessel. Imagine a public announcement in the year 2150. The world is introduced to the SS Odyssey, the first ship equipped with a functional gravity well drive. It does not travel to Mars by burning fuel, but by projecting a shallow, artificial gravity well a short distance ahead of its bow, gently sliding into the inner solar system as if sliding down a hill. Its hull is a shimmering composite that harmonizes with spacetime curvature, and its heart is a quantum computer that dances with the fabric of reality. This vessel is not for interstellar travel yet, but it proves the principle on a human scale, opening the solar system as truly and fundamentally as the first wooden ships opened the continents. This timeline is not a prophecy, it is a vision, a scaffold for our ambition. progress is never linear, and it will likely be an unforeseen breakthrough in an unrelated field that solves one of our most intractable problems. Yet, by mapping out the milestones, we give today's research a direction. Every experiment, every calculation, every new material synthesized is a step on this long road, a commitment to a future where humanity does not just cross the void, but learns to gently bend it to our will. The equations for warping space could one day be as fundamental as 2 + 2 = 4. To build the ships that reshape physics, we must first reshape the classroom. The next generation of engineers will not just learn Newton's laws, they will need to see the universe as a malleable fabric from their very first physics lesson. This demands a revolutionary overhaul of STEM education, one that intertwines foundational physics with computational thinking and creative problem solving from an early age. Educator Sal Khan, founder of Khan Academy, emphasizes the need for platforms that can adapt to these frontiers. He suggests that online learning must evolve to make complex topics like tensor calculus and quantum field theory as accessible and engaging as basic algebra is today. The goal is not to overwhelm young minds, but to invite them into the mystery, showing them that the deepest laws of the universe are puzzles waiting to be solved. Proposed changes begin in high school, where the principles of general relativity would be introduced not as an advanced, esoteric subject, but as the natural next step after understanding gravity. Students would explore thought experiments not about apples falling, but about tracing the paths of light beams as they bend around a hypothetical gravity well. The curriculum would actively foster a culture of what-if thinking, rewarding creative speculation that is rigorously tested, not just memorized answers. Hands-on projects would move beyond baking soda volcanoes. Imagine a classroom where students use simplified quantum computing kits to run basic simulations of spacetime metrics, or build tabletop interferometers to detect the subtle pressure of the quantum vacuum. This practical engagement makes abstract concepts tangible, transforming students from passive learners into active explorers. Yet, technical prowess alone is a dangerous tool. This new education must be fused with a deep study of philosophy and ethics. Every lesson on how to manipulate a gravitational field must be paired with a discussion on the responsibility that power entails. Students must grapple with the same cosmic dilemmas we have explored, learning to weigh the benefits of moving a planet against the potential for unforeseen harm. The ultimate expression of this educational shift is a university program in spacetime engineering. This is not merely a physics degree with a fancy name. It is a fully integrated discipline that combines advanced cosmology, materials science, and gravitational physics with the practical ethics of interstellar law. A student in this program would attend a lecture on the mathematics of closed time-like curves in the morning, and a seminar on the ethical implications of planetary manipulation in the afternoon. Their final project might be a collaborative simulation, designing a stable warp bubble while also drafting the safety protocols for its use within an inhabited solar system. The dream of silent ships that bend the cosmos will not be realized in our current laboratories. It will be built in the minds of the children we inspire today, in the classrooms we redesign tomorrow. The most critical component of any future starship is not a new alloy or a powerful reactor, but a curious, compassionate, and brilliantly educated human being. Our journey reveals a profound truth that the ultimate form of travel is not a journey at all. We began with a simple, radical idea that a spacecraft could stand perfectly still while the universe moved around it. We explored the principles that make this possible, from surfing waves in spacetime to canceling inertia itself. from harvesting power from the quantum void to screwing through the cosmos by spinning reality into a vortex. The consistent thread is a fundamental paradigm shift. We stop being objects that move through space and become architects who shape the very geometry of the journey. This is not merely a new engine, it is a new relationship with the cosmos. It offers the only plausible path to the stars that does not require us to break the laws of physics, but instead invites us to understand them more deeply, to work with the universe rather than against it. We are no longer just passengers on a vast and unforgiving cosmic ocean. We are learning to be its sailors, its cartographers, and in a very real sense, its co-authors. This redefines our place in existence. We transition from inhabitants of a universe with fixed rules to active participants in its ongoing creation. The cosmos becomes not just a place we visit, but a material we learn to sculpt. The visionary Carl Sagan once reflected that somewhere, something incredible is waiting to be known, that something might be the final, elegant piece of knowledge that teaches us how to gently, responsibly fold the stars themselves. If this vision of a future written not in rocket plumes but in the curvature of spacetime excites you, we would love to hear your thoughts. Share them in the comments below and subscribe for more journeys to the edge of what is possible.